how can technology help? So technology can help in several ways. One, it can help assess to find out where a kid's breaking down. How far back do I need to go with these guys? Technology is great for representing visual models to help connect their informal experience to something formal, to generalize that the fight they had with a sibling about, no, you're getting more than I am, to something there's a deeper understanding generally about what half of something means, or less or more than a half. We can help manage cognitive load. The research is very clear. We have a limited capacity in what's called working memory. Working memory is the part of the brain that works on tasks, but it gets overloaded very quickly. And so we need to help kids distribute processing power to other parts of the brain. That's one thing that fluency gives you. Fluency often means that I've taken something that used to be laborious, and you can think of any kind of task in your life. Think about if you have a little kid, or when you were a little kid, walking, how much focus there was on walking, or walking up and down stairs, or tying your shoes, but you do it over and over again, and all of a sudden, I didn't even think about it. There are a lot of things in our lives, our daily routines. Did I lock the car? Did I put on deodorant this morning? Did I put on deodorant this morning? The things that we do, they're almost automatic. And so by doing those things, by rehearsing them, by becoming fluent with them, we move it out of working memory and put it in a different part of the brain. And you can do these. They do these great studies where they take this. They've done them with vocabulary acquisition and with learning math facts, where when you introduce a new one and they put people in a functional MRI machine. Anybody ever had an MRI? Right, you go in this thing and you have to sit still while it's going clunk, 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 clunk. On a functional MRI, they give people a task, and then they measure what the MRI does is measures blood flow. And so when it's measuring blood flow in the brain, it's basically, that's an indicator of where activity is. Because the blood flows, there's an oxygen exchange, which involves iron, which is where the magnet part comes in. Anyway, when they do these functional MRIs and give people tasks, like learning a new vocabulary word or learning a new math fact, what they see is this activity in the area of working memory when a new task is being performed or a new word is being learned. And when it's been rehearsed and repeated, what you do is you see the energy, the activity, moving out of the working memory area and distributed to other parts of the brain. And what's interesting about the fraction study, that article that I showed, is that when they did these studies with fractions, the same area of the brain that lights up when people recognize whole number quantity is lighting up when people are recognizing a familiar fraction. It's like, oh, maybe it's all in the same place. People are recognizing quantity in the fractional and whole number quantity in the same way. So we want to help distribute, and the computer can help distribute and also reduce the demand. And I'll talk a little more about what this means. It can do this by adjusting difficulty and scaffolds, and I'll talk about that more in a second. Fluency through targeted practice. I was saying the goal is to help distribute, and so the computer can be really good about practicing to take the parts that you want to make fluent and helping redistribute the processing power in the brain. The immediate feedback part is really important because of kids' attitudes coming into math, and I'll talk about that as well. So let me drill down on these. So assessing kids in math. First, who has problems? So the idea, we need a screener for candidates in potential need of intervention. Somebody earlier was asking if I was going to show Scholastic Math Inventory. Scholastic, we have a new program coming out that's a general screener and progress monitor for kids. And in a class period, it gives you a sense of, is the kid where he's supposed to be, ahead, or in trouble? And you want to be able to identify who are the kids in trouble. And then when I identify those kids in trouble, I need to assess what that trouble is. A state test is tough. One item, as we saw, one or two items isn't enough to tell you what the problem is. Because often they'll get it right, or who knows, maybe they just weren't paying attention on that one. You need more than one or two items to really understand what's going on. And so let's focus on key areas like whole numbers, number sense, whole number computation, fraction concepts, to drill down. And we have this program Fractionation. We developed a placement assessment to kind of identify, to drill down a little bit in that area. And then that's going to tell you where do I need to rebuild. And the rebuild part is important as opposed to just these little tweaks. It's often more foundational than that. So here's an example. So this was actually 4 kids we were testing. All gave the same answers to these. And it's very similar to Pat. 4/15 plus 10/15, they said 14/15. Guys got it, right? So let's push them a little further. 3/8 plus 1/12, they said 4/20. Okay, maybe they don't have it. Same problem here. I can do it when the denominators are the same. When they're not the same, I'm not sure what to do. I'm not understanding what this is about. And what do? You fall back to what you already know. I know that when I add 8 and 12, I get 20. So it's blind procedure use. That procedure didn't work. I'm going to pick another procedure that I know. It's a little decimal. And we do this to kids. 72 and 1300ths minus 11 and 6/10 is 61 and 7/10. So these kids did, if this is 72.13 minus 11.6, then this makes total sense. 0.13 minus 0.6 must be 0.7. Because I'm doing the same thing on this side as I am on that side. If we use the language of 1300ths minus 6/10 and they have a concept of what those fractions mean, they're never going to say that's 7/10. But these guys are. Which is the correct answer to this problem? Same thing. 0.5 and 0.8, that must be 0.13. 5/10 and 8/10, that's a different story. But these kids all did the same thing. And how foundational, how fundamental is this? Which model shows 1/4 of the area shaded? Right? So 1 of 4 slices, that's one of the things, isn't it? That's a ratio, right? As opposed to 1/4 of the area. But this is not split into 4 parts. So there's a little leap there. They kind of have to get it to be able to do that. So it's pretty fundamental how far back we need to go with these guys. It's not like we just need to teach them the algorithm for decimals or the algorithm for unlike denominators. They need to know that too, but they don't get it. And if we give them the right language and we're consistent, we're much more likely for them to look and say, that answer can't be right. It has to be something else. Okay,